好，很棒。我们今天继续准备。这一次我记得把声音关掉，不然会有回音。
Execution bandwidth. We can utilize other computer architecture optimization techniques for the GPU register files. We could reduce the access latency by utilizing hierarchical approach to provide different access latency. We could also reduce the size by utilizing resource sharing. First, let's look at some GPU-specific register file usage characteristics. GPUs have many threads, but not all threads are active. GPUs use SPMD program model, and all threads have the same register file usage from the program's viewpoint. However, GPU execution is very asynchronous, so thread completion time varies a lot. Some threads might be finishing early, but some threads finish very late. An interesting part is that the register files in the finished threads are no longer needed. Furthermore, as we studied in the previous video lecture, divergent branches execute different paths of program, which might result in different register file usages. So register file usage pattern can be varied at runtime. Another observation is that not all registers are live. Live register means that the value in the register file will be used, and dead register means that the value is no longer needed. For example, add R1, R2, 1, and move instruction R2, 10. R2 value in the add instruction is no longer live because R2 value will be overwritten in the move instruction. So R2 register is dead after add instruction. You might think that this is not a big problem because in the CPU's world, add instruction and move instructions are typically executed back to back, just like in this illustration. However, in the GPU's case, the next instruction might be executed tens of warp instructions later. Here is an animation. First, we execute add instruction from warp 1 and page CUDA block 1, and then another add instruction from warp 2 and block 2, another add instruction warp 3 from block 3, and so on. We continue for a while until we execute add instruction from warp and block 1 again. So R2 in warp 1 block 1 is dead right after this first add instruction from the warp 1 and B1. And then the move instruction is executed a long time later from the same thread, warp 1 block 1, and R2 becomes alive at that moment. So this period between R2 is dead and alive can be very long depending on this scheduler's execution pattern. Contrary to just what I described in this slide, sometimes there might be very short distance between instructions. In a similar example, move instruction stores value 10 to R2 register, and the subsequent add instruction use the value of R2, and R2 value will be used immediately. If a scheduler schedules the next instruction immediately after move instruction, then hardware can reduce the time between storing R2 value. So then it also brings a question whether it is necessary to store the value 10 into the register R2. This problem gets even more worse because most register values are read only once. Similar example shows the R2 value has a 10, and then soon after, this R2 value will be overwritten after read only once. It was observed that almost 70% of register values are read only once on GPUs. This brings up question whether it is even necessary to store the value into a register file from the beginning, and can you just bypass this register value store? Based on these observations, several optimization techniques were proposed. The first optimization technique is using hierarchical register file. In this approach, there are two options to build hierarchical register files. In the first option is utilizing register file cache. Typically, smaller size of structure provide fast accesses. So smaller size of register file cache can store the value and provide fast accesses. And the main register file size can be even also smaller if we avoid storing all the values into the main register file. Sometimes the hardware decides to store all the values. In that case, the main register file size needs to be the same. But regardless of that, by having this hierarchical structure, we can provide fast access to the L0 or L1 register file and have a slow access for the main register file. This can even optimize further by having partitioned register file. We can use the different circuit technology to store slow and fast registers. We can even have using non-volatile memory to store large and slow register file to reduce energy consumptions. Another approach is to use register file virtualizations. Here we use virtualizations for research sharing purpose. Because, as we discussed it in the observations, not all registers are actually needed to store the values. So instead of having a register file for every single register items, we can have a small physical register file to store the actual value and only keep the namespace. By having separated namespace and physical register storage, we can still maintain the program characteristics, but we can have very small hardware features. So in summary, in this video, we observed several GPU programming characteristics and have learned several opportunities to optimize for registers. And the main lessons are, in several cases, not all registers are actively used. And we also have studied register file optimized techniques to increase the resource sharing and also to improve the latency. In this video, we'll continue GPU architecture optimization techniques by understanding unified register file and shared memory structure. The focus of these videos will be to explain optimization opportunities for unified memory and register file. We'll also learn how to differentiate between register file and memory, and we'll also review the concept of occupancy in GPU programming. Let's review the occupancy concept. In CUDA programming, the resource constraints affects the maximum number of blocks on each stream multiprocessor, SM. The shared memory requirements on register file size is a critical factor. For example, in hardware, each SM has 64 kilobyte registers and 32 kilobyte shared memory. In the one software example case, each block has 64 registers and no shared memory usages. In another software example case, each block has 4 registers and 2 kilobyte shared memory. In case 1, the shared memory will be underutilized because there is no shared memory usage. In case 2, register file size will be underutilized because at the end, 4 times number of total CUDA blocks and number of threads will be used for the register file size. So in this example, will be probably 2 kilobyte. So the question is, what if we have the shared memory and register file, and can it increase the occupancy? Before we answer the question, let's review hardware managed cache and software managed cache. In hardware managed cache, hardware decides which memory content will be cached based on LRU or other policies. And because not all memory contents will be stored, address text bits are needed to check whether an address is in the cache or not. On the other hand, in software managed cache, programmer specifies. So address tags are not needed because when a program says it is a software managed cache, that means that contents will be inside the memory or inside the cache. Let's also review register file and software managed cache.
我说我现在觉得过动症真的好恐怖哦，真的是好险小时候没有过动症，不然真的不知道怎么念书啊！我这样看感觉好像有很多个我。嗯，好吧，我们继续念好了。哦，不想念书，我疯了。
Software magic cache memes typically onto memory, which is very small. The common characteristics are both are storing data only, and both do not need to have a tag to check the address, and both the location indicates the address. And so we can just go to the particular location and fetch the content. The differences is the number of read and number of write ports can be different. Especially, register typically access two source operands per instruction, whereas a typical memory only accesses one address. Another benefit is in register files, access patterns are known as static time because these instructions knows which registers to access. So there could be more opportunities for the register file, even though register file requires more read bandwidth. The proposed solution is unified structures of shared memory and register file. The benefit is because we are sharing the structure, it could increase occupancy. But in order to do that, the critical requirement is high memory bandwidth. It should have sufficient port for read and write, and typically it is used bank structure, but now it needs to have more, even higher bank structures because register and shared memory have different access patterns. But this flexible resource sharing allows to reduce the resource constraints. Now we can consider the summation of register file size and shared memory size can be the constraint factor to decide the occupancy. So in summary, in this video, we review the differences between software managed cache and hardware cache and explore the benefit of unified memory and register file structure. And more kinds of this efficient resource sharing is needed for optimization of GPU performance and power.
这个的话，就是因为它这边多了一个，那就重复了，所以对啊，这边7会有8嘛，然后5它 reconversion point 是8，3的话，这个它到最后它也会到8，然后 D 也是。好，然后或者 key advantage different access latency，OK，对，有些比较快，有些比较慢嘛。 然后 main advantage of 这是什么鬼？Virtualization 它可以减少它的 overall size，因为它就不需要那么多空间来储存了嘛，它就是用一个暂存器，virtualization 虚拟化。Statement comparing blah 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 true，OK，他们都知道，然后是的，他们都会被限制，然后他们都比 global memory 还要快。然后因为 virtual software manager 它不需要 address tag，所以不用选它。Primary purpose。Dynamic verbs formation，反正就是更有效率吧，对吧？Correct 不是嘛，因为都会跑嘛，然后这个也不是。OK，所以 branch 有没有 branch 就是 dynamic verb formation，好不好？然后什么叫 divergence？就是因为它选了不同的 path，它就是 divergence。然后这个叫 branch。Average active，所以这就是它的 occupancy 啊，那个吧，occupancy 嘛，对不对？占有率，就是要尽量让它同时一起跑。对，to avoid bank conflicts。反正只要有 land，那就是要防止这个冲突，所以要用像甬道一样把它给封起来，它就不会撞在一起。Dynamic word formation, blah, 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 true, describe figure 10 in the paper. Fantastic. Fantastic. 完全没有看 paper. Crazy. 好不好？我们就来看这个吧，对不对？反正有个 paper 就说 来 Figure 10在哪里？是这吧？Figure 10这怎么样？完蛋了。Crazy！现在连这个 Chat GPT 都可以知道我的这个 Crazy。 加油加油加油！至少再看个3张吧，可以吧？可以吧？可以吧？所以 virtualization 的 paper 就是省电而已啦。Register renaming。啊。所以 unified 就容易会有 bank conflict 嘛，它是 reduce latency 嘛，然后这个应该是没有，应该是减少吧，因为它就不需要那么多，它其实就有点 cache 的概念，对 overhead，因为它每个都要准备嘛，然后 what the fuck。Work scheduler, blah 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 blah. Do you think benefit? Blah 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 blah. Do you spend conflict? 所以也是有一个分级的概念。哎，你看，所以 Chat GPT 也是会犯错，跟你一本正经的胡说八道。 downside.30分钟 ，Let's go。
In this module, we'll continue on GPU architecture optimization techniques. In this video, we'll explain the concept of GPU virtual memory and why it is essential in modern GPU architectures. We'll also discuss the challenges related to the GPU address translation, such as scalability concerns and managed uncoalesced memory accesses. Additionally, we'll explore opportunities for hardware optimizations in GPU address translations to enhance overall GPU performance and efficiency. Let's explore two key aspects of virtual memory: address translation and page allocations. In the CPU, the operating system takes care of page allocations. However, in the GPU, the process is slightly different. Initially, the CPU manages the pages in collaboration with the GPU driver. For memory allocation and data, in this module, we'll continue on GPU architecture optimization techniques. In this video, we'll explain the concept of GPU virtual memory and why it is essential in modern GPU architectures. We'll also discuss the challenges related to the GPU address translation, such as scalability concerns and managed uncoalesced memory accesses. Additionally, we'll explore opportunities for hardware optimizations in GPU address translations to enhance overall GPU performance and efficiency. Let's explore two key aspects of virtual memory: address translation and page allocations. In the CPU, the operating system takes care of page allocations. However, in the GPU, the process is slightly different. Initially, the CPU manages the pages in collaboration with the GPU driver. For memory allocation and data management, we rely on functions like CUDA-malloc, CUDA-malloc-managed, and CUDA-mancopy. These functions are used to allocate memory and facilitate the transfer of managed data. Let's review address translation. First, programmers write programs assuming virtual addresses, and these virtual addresses need to be mapped to physical addresses. There are several several key terms: VPN, virtual page number, PFN, physical frame number, or PPN, physical page number, and PO, page offset. In the address translation, VPN becomes PFN. Page offset stays the same. Typical common page sizes are 4 kilobyte and 2 megabyte. Pages are typically divided into fixed size chunks like 4 kilobyte or 2 megabyte. TLB, as a translation leukocyte buffer, is a cache to store address translation. TLB stores recently used address translation to speed up future accesses. Page table entry PTE stores mapping from VPN to PFN. PT itself is the memory, so accessing PT itself requires multiple memory accesses. Hence, TLB caches PTE so that it can avoid multiple memory accesses for PTE. TLB misses requires a page table access to retrieve address translation. If an address isn't found in the TLB, the page table must be accessed, which takes more time. Page fault occurs when no physical page is mapped yet, and then OS needs to allocate a page. Here is an example of 4-level address translation. Similar structures are used in x86, ARM, and even GPUs. The reason we have 4 levels is that if we didn't have any levels, the number of table entries would be equal to 2 to the power of the number of VPN bits, which is 2 to the 48th power. All the tables would need to be stored in memory, resulting in a massive number of entries. Hence, we use multi-level tables. When you use multiple levels, we don't have to store all the tables. The best case scenario would be 2 to the power of level 4 index bits, which is 12 bits, plus 2 to the power of the number of level 3 index bits, plus 2 to the power of the number of level 2 index bits, and finally 2 to the power of the number of level 1 index bits. This results in thousands of entries as opposed to a trillion number of entries. The downside is that the address translation needs to traverse through multiple levels of tables. First, it uses the level 4 index to access the level 4 table, and within the table entry, you will find the starting address of the corresponding table 3 entry. Then using the level 3 index bit, it accesses an entry in the level 3 table, which in turn provides a corresponding level 2 starting address. Continuing with the level 2 index bit, index the table, giving you the starting address of the level 1 table. This process repeats until we reach the level 1 entry, which finally stores the PTE containing the PFN number and other metadata. Using the PFN and page offset, the system can compute the physical address. Hence, with 4-level address translation, a single address translation requires at least 4 memory accesses. This process is often referred to as a walk. Address translation can be performed by hardware through a hardware page table walker, which is called PTW, or by software. Now, let's discuss GPU virtual memory. In earlier GPUs, there was no virtual memory, or it has only one-to-one mapping. As GPUs have become more programmable, new page table entry address. Now, let's discuss GPU virtual memory. In earlier GPUs, there was no virtual memory, or it has only. Problem is requires a page table access to retrieve address translation. If an address isn't found in the TLB, ARM, and even GPUs, the number of entry level 2 then through a hardware page table walker, which is called PTW, or by software. There was no virtual memory, or it has only one-to-one mapping. As GPUs have become more programmable, the need for complex memory system support has risen, such as unified virtual address. Address translation shares similar mechanisms with CPUs, except for address coalescing. The memory addresses stage is divided into address coalescing and TLB accesses. If a TLB miss occurs, the page table walker retrieves a new page table entry, or the TLB miss handler manages the TLB misses. Typically, L1 cache accesses use virtual memory addresses, while L2 cache accesses use physical memory accesses. Typically, L1 cache accesses use virtual memory addresses, while L2 cache accesses use physical memory addresses. Let's consider an example where we assume a page size of 256 bytes. In the previous Typically, L1 cache accesses use virtual memory addresses, while L2 cache accesses use physical memory addresses. Let's consider an example. Typically, L1 cache accesses use virtual memory addresses, while L2 cache accesses use physical memory accesses. Typically, L1 cache accesses use virtual memory addresses, while L2 cache accesses use physical memory addresses. Let's consider an example where we assume a page size of 256 bytes. In the previous example, the first load, which using R1, generates one memory request, which results in one TLB access. Similarly, the next load generates only one TLB access with tag 00. In the second example, multiple memory requests, 8 of them are generated, but they won't be coalesced. Each of them generates separate TLB accesses. If we examine the TLB address tags, the first two addresses are actually combined into one TLB access, but the rest are separated TLB accesses. Therefore, one memory instruction ends up generating 7 TLB accesses. In uncoalesced memory accesses, the total number of TLB requests from one warp would be the same as the number of width of a warp. The challenge in GPU address translation lies in achieving scalability. A single warp TLB miss can lead to the generation of multiple TLB misses, particularly in case of uncoalesced memory accesses. Hence, the critical factor is having high bandwidth of the PTW, and one option is sharing a high bandwidth PTW across multiple SMs. Let's discuss techniques to reduce address translation cost, which can include segment mapping, large page sizes, and the concept of multiple levels in TLB hierarchies. In segment mapping, each virtual address space corresponds to a portion of the physical address space. For instance, each program requires address space from 0x0000 to 0xFFFF. We assign the orange area 0x000000 to 0x00FFF to program 3, and the blue area to program 2, and the green area to program 1. With this arrangement, during address translation, we can simply add the upper 2 bits, 0, 1, or 2, to access physical addresses, resulting in very low-cost address translation. The figure on the right slide illustrates two levels of TLB hierarchies. Typical page sizes is 4 KB with 2 MB pages. And in this case, the number of VPN is reduced from 51 bits to 42 bits. The number of TLB entries also reduced by 512. However, there is a downside to this approach, which is memory fragmentation. For example, if only 1 KB of memory is needed, the system uses 4 KB paging, it weighs 3 KB of memory. This contrasts with the case when you use 2 MB memory system, it weighs 2 MB minus 1 KB. In summary, memory address coalescing plays a critical role in address translation. Furthermore, ensuring scalable address translation is most important, which includes aspects like resource sharing and the use of large pages. In this video, we'll continue studying GPU virtual memory. By the end of this video, you should be able to explain Unified Virtual Address Space, UVA, and you should be able to explore challenges associated with on-demand page allocations. Let's review the host code of CUDA. We can see 3 API calls, CUDA malloc and CUDA mancopy. Here, CUDA malloc allocates memory in the GPU, and CUDA mancopy transfers data between CPU and GPU. Let's discuss deeper into GPU page allocations. In earlier GPUs, they follow the copy then execute model. This model involves copying data from the CPU to the GPU before executing a kernel. It utilizes functions like CUDA malloc for GPU memory allocation and CUDA mancopy for data transfers. This ensures that all necessary data is available on the GPU for computation. This implies explicit data transfer. Data must be explicitly moved between the CPU and GPU before launching a kernel. The benefit includes efficient PCIe bandwidth usage, allowing programmers to optimize PCIe bandwidth. It's a part of pre-kernel preparation, where GPU drivers set up and data management occur before kernel execution. The downside of explicit page management is that it requires programmers to manually manage memory pages, which can be complex. Unified Virtual Address Space. In UVA, CPU and GPU share the same address space. This approach is commonly used in the OpenCL CUDA programming model and is known as SVM, Shared Virtual Memory. UVA increases programmability. SVM enhances programmability by allowing both the CPU and GPU to operate within the same address space. However, this approach requires dynamic page allocation to manage memory efficiently. On the other hand, the separated memory space permits efficient bulk data transfer, making full use of PCIe bandwidth. This is illustrated in the left figure. Logically, there are two buffers, one for CPUs and one for GPUs. In the case of UVA, logically there is only one buffer, and it can be accessed by both CPUs and GPUs. For separate memory space, Logically, CPU writes only to CPU buffer, and GPU writes into only GPU buffer, and then there needs to be explicit copy. However, in the UVA, those explicit copy are not needed. However, most GPUs are discrete GPUs in the modern high-performance computing, which has a separate physical memory system. To support UVA in a discrete GPU setup, there needs to be a copy between CPU memory and GPU memory, which involves dynamic memory management. The CUDA-Mallow managed API handles this, and this is also called on-demand memory management. The GPU generates a page fault, and that request needed to be sent to the CPU. The CPU's operating system and GPU's driver handles this page fault and then send the information back to the GPU. Consequently, the latency can be in the range of tens of milliseconds. Let me briefly provide a background on IO-MMU. IO-MMU, which stands for Input-Output Memory Management Unit, serves as a bridge between input-output devices and the memory management unit. Its primary function is to enable direct memory accesses, DMA accesses, using virtual addresses. This means that it allows for I/O virtualization by utilizing virtual addresses for DMA operations instead of physical addresses. Both the CPU and GPU are equipped with their own IO-MMUs. In the case of a GPU, each virtual page management is seamlessly integrated into this unit. Previously, GPU memory was solely managed by IO-MMU, as the GPU memory was treated as peripheral devices. However, with the UVA, not only the IO-MMU, but also the CPU actively involved in the management. What are the challenges of on-demand GPU memory, which is crucial for UVA? GPU page management is performed by the host processor. Retrieving page mapping from the CPU's IO-MMU can be costly, involving the overhead of PCIe communication and the CPU's interrupt service handler. This process often takes several tens of microseconds. Certain techniques can help reduce overhead of on-demand memory allocation. For instance, we can employ techniques like on-demand or prefetching of pages to predict future memory addresses and bring them in advance. Another approach is shift page mapping management to the GPU side instead of CPUs. Additionally, cooperative effort between CPU and GPU driver can be beneficial, with the CPU handling large memory chunk, while the GPU manages small pages within the same large chunk. Let's look at the background of memory prefetching. Memory prefetching is a technique that involves predicting future memory accesses and fetching them in advance. For example, if we have a sequence of memory addresses like 0x0123, the prefetching mechanism would preemptively fetch the next addresses such as 0x04 and 5. To illustrate this concept, consider the example of vector addition and the CUDA version of the code is shown here. When accessing element in an array A and B using an index IDX, these accesses are typically done sequentially. Therefore, array A and B are good candidates for prefetching. Similar to memory address prefetching, we can also apply this concept to page prefetching. This involves using sequential address predictions such as 0x0123 and so on to 0x100. To simplify the example, a page size is again 512 bytes instead of 4 kilobytes. Here, page addresses can often be easily predictable, as shown in this illustration. So we can prefetch pages 1, 2, 3, and so on. However, it is important to note that the execution order of GPU thread block is not necessarily sequential. For example, in the illustration here, each color represents data accesses from different thread blocks, highlighting their concurrent and non-sequential execution. To address this issue of out-of-order execution of thread blocks, NVIDIA employs a tree-based neighborhood prefetching approach. Initially, it divides a 2 MB chunk into two 1 MB sections, then it creates 64 kilobyte nodes within these sections. If a page fault occurs within a node, the system fetches entire 64 kilobyte. Another node, if there is a page fault, it fetches all 64 kilobyte again. If multiple nodes generate prefetch request, it fetches the upper node of page, which becomes 1 megabyte. This way, it detects spatial locality, but also limits the size of prefetched blocks. GPU memory oversubscription. It becomes an issue when allocating an excessive amount of virtual memory space to GPUs. This situation often leads to page eviction, as there are not enough pages to accommodate the demand memory request. The question then arises, which pages should be evicted? Prefetching plays a critical role in addressing these challenges. As the demands on GPU kernel memory continues to increase, the problem of GPU memory oversubscriptions becomes even more pressing. In summary, this video highlights several challenges in unified virtual address space UVA management and underscores the importance of employing page prefetching techniques to tackle these challenges. It also touches upon the comparisons between on-demand memory allocations and the copy and execute model. In this video, we'll discuss GPU warp scheduling. Our learning objectives for this video include gaining a solid understanding of GPU warp scheduling policies. We'll explore the various challenges and considerations that come into play when it comes to GPU warp scheduling. Additionally, we'll explore different scheduling policies, including round-robin and GTO, to get a comprehensive view of this topic. We discussed GPU pipeline before, which is fetch, decode, register file access, and scheduler, and so on. So far, we discussed it as if there is only one warp ready to be scheduled at a time. But what if there are multiple warps that are ready? Like in this example, there are 4 warps that are all ready, which you want to choose to schedule. This is a warp scheduler's job. Let's begin by discussing the CPU instruction scheduler. In the context of CPU instruction scheduling, it selects from the available ready instructions. This process involves examining all instructions in the scheduler, especially those that cannot be divided into multiple cycles. Within CPU instruction scheduling, several policies come into play, including oldest first, critical instruction first, And as an example of critical instruction first, there are load instructions first and instruction with many dependent instructions first. For example,
快顶不住了。我刚看到一个文章，然后舌头吐出来40秒钟，可以降低压力。不然我们来试试看。好像真的有用哎。好，我们继续看。好累哦，怎么办？这就是过动症吗？看书都想睡觉。啊，怎么办？录影这样上得了哈佛吗？啊，完蛋，完蛋。我们把7之3上完，然后我们休息一个大的。
load instruction first policy. It proves usefulness in generating memory requests as soon as the load address becomes ready. Additionally, prioritizing instructions with many dependent instructions can lead to other dependent instructions become ready sooner. The GPU warp scheduler implements an in-order scheduler. However, even though it's an in-order scheduler, when there are multiple warps ready, he selects and executes whichever warp is ready. Hence, if you examine the final execution of instruction stream, they all appear to be out of order execution. Let's discuss the two most basic GPU warp scheduling policies, which are round-robin and GTO, greedy than oldest. In this example, there are 3 instructions, each represented by a different color for different warps. In the round-robin, it selects one instruction from one warp in a round-robin fashion, like this. The third instruction, which is a memory instruction, generates a cache miss, and then switch it to another warp, and so forth. Hence, all 4 memory requests are generated almost simultaneously. Therefore, the latency cannot be hidden. So the pipeline has a stall, and once the first memory request from the warp 1 returns, it resumes execution, and then continues. On the other hand, GTO starts with only one warp initially, the oldest one, and then it switches to another one when there is a long latency event, such as cache misses, branches, or lengthy tensor core operations. In this example, the memory address generates a long event, and whenever there is a cache miss, it switches to another warp. 1, 2, 3, and then 4th. In this case, it actually generates the memory request from the first warp early enough to reduce the overall start cycles, but benefit depending on the specific program characteristics. The challenge for the scheduler is that it has to prove to be determined which instructions are ready. The task actually consumes a significant amount of power. Hence, in a single level scheduler, it needs to search the entire scheduler queue just to schedule only one instruction. To reduce this inefficiency, a 2-level scheduler was proposed. In the 2-level scheduler, the verbs are divided into two groups, pending verbs and active verbs. The scheduler only searches the active verbs queue and choose one from there. Another interesting aspect of the verb scheduler is impact on cache behavior. Let's assume there are 4 verbs and each verb repeatedly accesses the memory addresses A1, A2, A3, and A4. The diagram illustrates the round-robin scheduling policy and the memory addresses. Suppose there is a cache, but it can only accommodate 3 blocks. Due to the LRU replacement policy, when the 4th verb accesses A4, it evicts A1. Then when A1 is needed again, it results in a cache miss and evicts A2, but inserts A1. This pattern continues, resulting in cache misses for all blocks. Now let's consider the GTO scheduling policy. It brings A1, and A1 remains in the cache. When it's time to start verb 2, it brings A2 and inserts into the cache. Again, A2 will be in the cache for the rest of the verb execution. This repeats for all 4 verbs. Hence, in the GTO scheduling policy, only compulsory misses occur, which is an ideal scenario. The important part is that the verb scheduler's decision can have an impact on the working set size of the L1 cache. To make this previous example more formal, let's assume if each verb is working set size is SSW and there are n verbs in a SM, the working set size for round-robin scheduling policy will be SSW times n. However, if we limit the number of scheduler verbs to SW, then it would be SSW times SW. It is important to note that in the case of GTO, SW may not necessarily be equal to 1, as GTO may schedule to another verb in the event on a long latency instruction. A cache-aware scheduler limits the number of schedulable verbs to a small quantity. In the GTO, when encountering a stall, it selects verbs from verb 1 to 3 and then it switches to another verb. However, in the cache-aware scheduler, it selects instructions from verb 1 to 3 and once they are completed, it processes to schedule instruction from verb 4. The challenge lies in case where a program involves thread synchronization, as it must ensure that all verbs are executed. Another challenge is determining the appropriate number of active verbs to schedule. In general, having more verbs increases parallelism. However, by limiting the number of verbs, it might reduce the cache working set sizes, but it also restricts verb level parallelism. Consequently, depending on the cache behavior and program characteristics, the optimal number of active verbs needs to be selected. Here are some other verb scheduling policies. We have the prefetching aware verb scheduler, which is built upon the two-level scheduler, as discussed in Zhang's work. The scheduler operates on the concept of fetching data from non-consecutive verbs with the goal of enhancing bank-level parallelism. Another approach is a CTA-aware scheduling, also presented by Zhang. CTA-aware scheduling takes into account the characteristics of cooperative thread arrays and provides control over which CTAs are scheduled. In summary, we've covered scheduling policies like round-robin and greater than oldest. We learned that implementing a two-level verb scheduler can lead to substantial energy savings. The verb scheduler's choices can influence the effective working set size, with the cache-conscious scheduling policy being one example. Additionally, we've explored various other opportunities for scheduling optimizations. The wide control over which CTAs are scheduled, verb level parallelism. Consequently, depending on the cache behavior and program characteristics, the optimal number of active verbs needs to be selected. Here are some other verb scheduling policies. We have the prefetching aware verb scheduler, which is built upon the two-level scheduler, as discussed in Zhang's work. The scheduler operates on the concept of fetching data from non-consecutive verbs with the goal of enhancing bank-level parallelism. Another approach is a CTA-aware scheduling, also presented by Zhang. CTA-aware scheduling takes into account the characteristics of cooperative thread arrays and provides control over which CTAs are scheduled. In summary, we've covered scheduling optimization.
好，我们来做题。小镇做题家。What are the primary roles of the page table walker？ 反正就是它是要找 memory 的，所以是从 PTE 里面找的。这个又是什么意思呢？1 GB 是2的30次方 bytes。48减30，然后就是48减掉30，所以1 GB 是因为是2的3次方是8嘛，对不对？8 bits 等于1 byte 嘛。好，就这样子。unified 嘛，对不对？哦。benefit reduce energy consumption. Okay. Benefit of 都已经说是 on demand 的嘛，所以就是 dynamic 嘛。
In this module, we'll study GPU modeling and simulation techniques. The learning objectives of these videos are to describe cycle-level performance modeling for CPUs and GPUs, and also to explain queue-based performance modeling. We also want you to understand the basic simulation code structures for CPUs and GPUs. This video is for you to get ready for the architecture modeling programming project. There are several performance modeling techniques: cycle-level simulation, event-driven simulation, analytical model, sampling-based techniques, database statistical and ML modeling, and FPGA-based emulation. We'll provide a brief introduction of these techniques. First, cycle-level simulation. This is commonly used in many architecture simulators, especially for the all-your-hardware design time. In the cycle-level simulation, a global clock exists. In each cycle, events such as instruction fetch and decode are modeled. Multiple clock domains can exist, like memory clock, processor clock, and network-on-chip NOC clock domains. In the cycle-level simulation, two types of simulation techniques exist: execution-driven versus trace-driven. In the execution-driven, instructions are executed during the simulation. Depending on when an instruction is actually
九斗，想起来了，回
executed inside the simulator, there are also two different simulators: execute at fetch versus execute at execute. Execute at fetch means instructions are executed when an instruction is fetched. Execute means instructions are executed at the execution stage. Most of the time, this difference is not noticeable, but as execution-driven simulator designers, this decision has to be made. Trace-driven is based on traces, and here, because traces are collected in advance, simulations and executions are decoupled. Benefits of execution-driven is there's no need to store traces, and it can also model behavior that vary at runtime. On the other hand, trace-driven cannot model runtime-dependent behavior, such as lock acquire and barriers. In general, trace-driven simulators are simpler and often lighter, so it's easier to develop. Also, you can just collect memory traces only for memory simulations or cache simulations. In the cycle-level simulations, queue-based modeling is often used. In the 5-stage pipeline, between pipeline stages, we'll have queues except for scheduler. Here in this diagram, green box shows the queues, and this illustrates how we model 5-stage pipeline using queues. Instructions move between queues. Scheduler select instructions that will be sent to the execution stage among ready instructions. Hence, it is not implemented as a queue structure. Other queues are FIFO structures. When an instruction is complete, the dependent instructions are ready. The dependence chain needs to be modeled, and broadcasting also needs to be modeled, just like the actual hardware. Cache and memory are modeled to provide memory instruction latency. Execution latency can be a simple lookup table to find the latency if the latency is not dependent on runtime behavior. Then let's discuss how to set up modeling parameters when we use queue-based modeling. The number of cycles in each pipeline stage is simply modeled by the depth of the queue. How many instructions can move between queues represent pipeline's width, such as each execution bandwidth. At this moment, you might wonder how we should know the latency of each instruction that we can model. You might wonder whether we need a circuit-level simulators to find the latency. The answer is we don't need to measure the instruction latency. Instruction latency is given as a parameter, such as add instruction takes 1 cycle and multiply instructions takes 3 cycles. Latencies can be obtained from literatures, or we could use more detailed simulators like a Cacti or RTL. There are many public documentations that discuss such instruction latency. Here is an example of 5-stage processor modeling code, which is from a Maxim, a CPU and GPU simulator that is developed from Georgia Tech. In the main function, it instantiates Maxim simulator. In the simulator, first it initializes the parameters. After that, it starts to call run a cycle of the simulator until the simulation can end. Inside the maximum module's runner cycle, it increments cycles. Then it goes through CPU, memory, NOC runner cycle. In the CPU runner cycle, it goes through each pipeline's runner cycle. The simulator is also built on hierarchical modules. Each modeled instruction has an op data structure. The op structure will go through the pipeline, from the front end to the decoder stage, to scheduler, and execution, and write back, and then retires. This op data structure tracks instruction progress and cycles. For example, done cycle in op data structure indicates the done cycle by adding schedule time and instruction latency. Done cycle indicates when an instruction is completed. When the processor schedules an instruction, at that time we can know when an instruction is completed if the instruction has a fixed instruction latency. So when the scheduler is executed, it can compute this done cycle. The exception is if the latency is not fixed, such as cache misses. In that case, we use cache simulations, which models cache hit and misses. Then we can know the memory instruction latency, and based on those instructions, we add the latency into the done cycle. The role of scheduler is to identify read instructions. Scheduler also needs to handle resource constraints. For example, even though there are multiple instructions already, it should schedule only the instruction that can be executed for the given resource. For example, number of floating point instructions, number of load and store queues, execution width, ports in the cache systems. If an instruction takes multiple cycles, the resource contention should be also considered that. It should ensure that resources are available for multiple cycles. Now let's talk about how to model GPU cycle level modeling. In some sense, it is similar to CPU modeling. One of the biggest factors is the simulation execution unit is a verb instead of thread to model SIMD behavior. So verb instruction is modeled for fetch, decode, schedule, and execution. Scheduler chooses instructions from the head of each verb because it is an in-order scheduler. The difference from CPUs is it's an in-order scheduling within a verb, but it can be an out-of-order execution across verbs. Major differences between CPU and GPU in terms of modeling are first handling divergent verbs, and then verb, thread block, kernel concepts should be implemented to reflect GPU execution model. And scheduler also needs to be modeled significantly differently. Now let's discuss the end of simulation. First, entire thread block scheduled to one SM. The simulator needs to track complete thread, which means end of the program instructions. When all thread within a CUDA block completes, the corresponding CUDA block completes and can be retired. When all thread block is completed, the corresponding kernel ends. When all kernel ends, the application ends. So the simulator also needs to follow the execution hierarchy. In summary, in this video, CPU and GPU cycle level simulation techniques are reviewed. We also reviewed how to model latency and bandwidth using queues.
我今天先这样子，准备休息啊，大脑休息一下，太累了。好啊，先这样子，大家拜拜。